Divyesh? Divyesh?
Yes, Upadik.
Yeah, so maybe you can unmute yourself and also start the video because we'll put your video in the spotlight mode in the YouTube channel feed.
I've done that.
Okay, let's see. Yeah, okay. Let's check the YouTube feed. Yeah, it's working fine. Okay, so are we ready to go? Uh, Divyesh?
I'm ready. Yeah.
Okay. Okay, so welcome everybody to the second day of the Indian SAT and SMT School 2020. So yesterday we had very interesting session where Ashutosh Gupta first talked about the uh, basics of logic and just to get everybody ramped up on that. And then, of course, Professor Armin Beer gave an amazing three-part tutorial where he walked us through, starting from very basics, he walked us through the uh, some of the more subtle details about modern SMT solvers. So today we have a pre-lunch session which will consist of two talks. One will be given by Divyesh, who will talk about the full program induction technique, and the second will be given by Professor Kuldeep Meal, who will talk about Ganak, which is among the most powerful exact model counters available today. And after that, in the afternoon, we are going to have Martin Nick's brain talking about SMT solving with specific theories, and I think this will be very useful for those who are using SMT solvers for uh, floating point and all of that. So with that, let's get started. It's my pleasure to introduce Divyesh Unatkar. He is a PhD student in the Center for Formal Design and Verification of Software at IIT Bombay. He's currently pursuing his PhD in software verification under my supervision and under the supervision of Professor Ashutosh Gupta. His work focuses on proving properties of programs that manipulate arrays. He's also affiliated as a researcher with the Foundations of Computing Group, TCS Research, Pune. So over to you, Divyesh.
Thank you, Professor Supratik, for the introduction. Hello, all. So today I'm talking about this technique that we call full program induction. So let me get started. Programs that manipulate arrays are very common, especially in embedded and safety critical applications. Consider the function polycompute as an example program. In such programs, arrays are of parametric size, say n. There are multiple loops that update arrays. The value computed in an iteration may depend on values computed in previous iterations. The statements in each loop iteration may not execute in parallel because of complicated data dependencies across iterations. We want to be able to prove quantified as well as quantifier-free properties of such programs. The quantified post condition here says that the array element at the kth index has the value k cube for all values of k in the given range. The precondition here is true. That is, it does not constrain the values of any inputs. The program parameter n takes positive values greater than 0. The question that we want to answer here is, given that the precondition evaluates to true and this program completes execution, does the postcondition evaluate to true for all possible values of n? That is, does this parametric hold triple phi n p n psi n hold for all values of n, where phi n represents the precondition, pn is the program with parameter n, and psi n is the given postcondition. Several tools and techniques try to answer this question. Synthesis and use of loop invariants is one of the most popular techniques in this arena. However, generating loop invariants is a non-trivial task, especially when loop invariants are quantified and they have multiple arrays and non-linear terms. Techniques that use abstraction tend to lose precision in presence of complex data dependencies in array elements. Techniques that rely on solving recurrences as well as fixed point computation are unable to solve such programs. None of these tools or techniques highlighted here are able to solve our motivating example. This motivates us to come up with a technique that can handle these kind of programs better and efficiently. Let me give you a pictorial overview of our technique. At a high level, full program induction technique works like any other inductive technique, but instead of inducting over individual loops in the program using the loop counter, it inducts over the entire program via the program parameter n. In the base case, we prove this whole triple for small values of n, say n is equal to 1. If the base case fails, a true counterexample is obtained, and we report a property violation along with that counterexample. As the induction hypothesis, we assume that the entire whole triple with parameter n minus 1 holds. Now, in order to make use of such an induction hypothesis, which is a whole triple, in the inductive step, we need to relate the validity of the original whole triple with the induction hypothesis. That is, we need to relate the program with parameters n and n minus 1 as well as the preconditions. We have come up with the novel concept of a difference program denoted by delta Pn. It is a code fragment which, when executed after the program with parameter n minus 1, results in the same state as the program with parameter n. We have also come up with this notion of difference precondition denoted by delta phi n. It represents the part of the formula that is not affected by the computation of Pn minus 1. Once these two artifacts are automatically computed, we can proceed with the inductive step. In the inductive step, assuming that the post condition coming from the inductive hypothesis evaluates true and the difference precondition evaluates to true, we want to check if the post condition evaluates to true after the difference program has been executed. If the inductive step succeeds, then we conclude that the given post condition holds. However, this may not be the case always. That is, the difference program may refer to variables whose value is not qualified by the formulas shown here. In such a case, we infer new proof subgoals and subsequently try to establish those subgoals. Let me take you through the details of that. So we use Dijkstra's weakest precondition computation to infer a new formula denoted as pre n minus 1. So the weakest precondition of psi n over the difference program delta Pn is pre n minus 1. Such a formula is used to strengthen the precondition of the difference program. This formula must hold after the hypothesis program, that is Pn minus 1. Since it must hold after Pn minus 1, the formula pre n must hold after the program Pn. That is, the inferred formula simultaneously strengthens the precondition and the postcondition of the difference program. Now we need to establish the validity of the strengthened postcondition. We again start with the base case where we set n with a small value, say 1 here. If this base case fails, then we again use the weakest pre-computation to try and infer a new formula pre-prime n. Alternately, we also consider splitting the originally inferred formula pre-n, as well as we consider splitting the difference precondition. I'll not go into the details of the splitting. Please refer to our paper for that. Once the base case succeeds, we move to the inductive step. In the inductive step, we assume that the strengthened precondition evaluates to true, and we want to prove the strengthened postcondition after the difference program has executed. If the inductive step succeeds, then we conclude that we have proved the given postcondition. However, this may not always be the case, since there may be some more variables which are referred in the difference program that are still not qualified by such a formula. In such a case, we try to infer some more new subgoals. Again, we use the weakest precondition computation for inferring new subgoals. This precomputation is over this strengthened postcondition, that is conjunction of pre-n and psi n. So here the formula pre2 n minus 1 is the formula that is inferred by computing the weakest pre of pre1 n and psi n over the difference program. We may not always be able to compute such a formula. In such a case, we remain inconclusive. If we are able to compute such a formula, then it strengthens the pre and post condition simultaneously, and the steps outlined are repeated again. We continue in this manner until the post condition is established. Let us try to apply this technique to our motivating example. So here I have again taken this polycompute function that we have already seen. We'll start with the base case where we substitute n with 1. We assume that all the loops now have a finite bound and thus can be totally enrolled. This is required so that we can feed this program to a bounded model checker or an SMT solver. Here, the post condition says that the value of the array element C of 0 is 0 cube. From the program, it is clear that that is true because C of 0 is set to 0. Thus, the base case succeeds, and we proceed to the inductive step. In the inductive step, we assume that this formula is available from the induction hypothesis. This is psi n minus 1. We need to compute the difference precondition, delta phi n. Since phi n is true here, the difference precondition is also true. We also need to compute the difference program. Note that here, the difference program is just the last iteration of all these loops. And we want to establish the given postcondition. Now, the given precondition already implies part of the postcondition. So we only need to establish that Cn minus 1 is n minus 1 cube. Note that this inductive step cannot be immediately discharged because the array element Bn minus 2 is not qualified by the precondition available here. Hence, we try to infer a new formula by computing the weakest precondition. Such a formula is naturally lifted to its quantified form by quantifying out the program parameter n. So here, I have shown such a quantified formula that we obtained from the inferred predicate. This formula strengthens the precondition, and we again need to establish that it actually holds. So as outlined, we again start with the base case for this inferred formula. It says that b of 0 should be equal to 1 cube minus 0 cube, that is 1. That is clearly set in the program, that is b of 0 is 1. So again, the base case succeeds for the inferred formula. And we strengthen the postcondition as well with this inferred formula. Now we also need to establish that b of n minus 1 is n cube minus n minus 1 cube. So again, the inductive step does not succeed directly because a of n minus 2 is not qualified. So we compute the weakest precondition again and infer a new formula marked as pre2 here. And we again naturally lift it to its quantified form by quantifying out the program parameter n. Again, we need to repeat the base case for this inferred formula. So I have substituted n with 1 in the quantified formula. And the base case succeeds for this. That can be independently verified. After the base case, we again move to the inductive step. Now there are no more array elements or scalar variables that are referred, which are not qualified in this computed precondition. And the inductive step can now be discharged. In order to aid the SMT solver, we eliminate the quantifier from the inferred precondition formulas. In order to eliminate those quantifiers, we instantiate them to the indices that are already referred in the difference program. So I've shown such an instantiation here, where the quantifiers are now eliminated. This whole triple is encoded as an SMT constraint, and now Z3 establishes the validity of this whole triple. Note that during this entire process, we did not compute or make use of loop-specific invariants. I'll briefly touch upon the method for computing these components, difference precondition and the difference program. Computing the difference precondition requires that we satisfy these two conditions. That is, the difference precondition in conjunction with the precondition of the induction hypothesis is implied by the original precondition. That is, your conjuncted pre is weaker than whatever precondition that you started with. and that the difference precondition is not impacted by the computation of Pn minus 1. So there is an easy test for existence of such a precondition. Only if phi n implies phi n minus 1 holds, then we are guaranteed that such a difference precondition can be computed. On a successful validity test, we compute the difference precondition by looking at the shape of the precondition that is already given to us. If the given precondition is a universally quantified formula, then the difference precondition is just the instantiation of the quantified variable with the values in the difference coming from the bound. For example, given the precondition for all I where I is in 0 to n, a of I greater than 0, phi n minus 1 is for all I where I in 0 to n minus 1, a of I greater than 0. So the difference in the range is n, and hence the difference precondition is a of n greater than 0. If the given precondition is a conjunction of different formulas, then we compute the difference precondition as the conjunction of the difference of the individual conjuncts. In all the other cases, we conservatively assume that the difference precondition is true. Computing the difference program is a bit involved. I'll still highlight important points here. We first peel all the loops in the difference program with the number of difference iterations in Pn and Pn minus 1. Subsequently, we transform the assignment statements in these peeled loops with difference statements. So this is how the difference statements are computed. So if your statement is a of I is equal to a constant, then it is transformed to a statement which says the value of a of I is equal to the value coming from the program Pn minus 1, denoted as shown here, plus the difference in the value of this constant. Such difference terms are subsequently simplified, and the loops containing only such assignment statements are sliced off. Here is another example. So the idea of computing the difference program is try to come up with a program that is loop free. So the difference is essentially loop free. If still there are loops in the program, we try to accelerate those loops whenever possible. If the loops cannot be accelerated, our technique can be restarted by making the difference program as a new program under analysis. Please do refer to our paper for more details regarding computing the difference program. Our technique is sound, and the following theorem guarantees its soundness. Suppose that the given program Pn can be decomposed into a sequence of programs Pn minus 1 and the difference program, and that there exists a difference precondition that satisfies condition A and B, as we have already discussed, and that there is a formula pre-M that can be inferred such that the base case holds for the given post condition as well as for this inferred formula pre-M, and the inductive step succeeds, then we are guaranteed that the given whole triple holds for all values of n greater or equal to 1. We have implemented this technique in a prototype tool that we call Vajra. It passed the artifact evaluation at Takas. The tool can be accessed at this link. We have evaluated our tool on more than 200 programs. All the programs are now a part of SVComp. As we can see, the tool was able to prove the property in most of these programs or prove the program unsafe whenever that was the case. It was inconclusive in several cases when we could not compute the difference program because the original program had a branch condition where the condition's value was dependent on n, or we could not compute uh, the formula pre by using Dijkstra's weakest pre-computation. We have compared our tool against several state-of-the-art tools such as VIAP, a version of Variabs, Booster that accelerates array programs, Wafer that deploys interesting abstractions, as well as FreeCon that infers invariants from CHC programs. We manually translated all the input programs in the format that these tools required. A timeout of 100 seconds was imposed. So here are some of the results from the paper. On several programs, our tool was able to discharge the post condition within a second, whereas the other tools, they struggled to prove the post condition. There are also programs where we could prove it efficiently, whereas other tools could prove, however, they took more time. Also, there are programs where we could not conclude whether the post condition holds or not, however, other tools were able to. These are the cases where we could not compute the difference program or infer an interesting formula using weakest pre-computation. Also, there are programs where none of the techniques are conclusive. We participated in SVComp last year, and this participation is via the tool Variabs. Variabs is an industry-leading verification tool from TCS Research. Our tool is bundled with version 1.4 and above. So Variabs won a gold medal in read safety category, and Vajra was instrumental in improving the score in the arrays subcategory. So in the year 2020, we were the best performing tool in the arrays subcategory. We scored 694 points of 759 points by solving 410 programs out of 436. The next best tool scored 379 points. So there is a huge gap that can be seen. In the previous year, we were ranked second in the arrays subcategory. So there is a competition contribution paper in the SVComp track at Takas, where more details can be found regarding this integration. Please do refer. To conclude, I presented a property-driven and efficient verification technique that can prove quantified as well as quantifier-free properties. It computes the difference of the program and the precondition during the inductive step. We use the weakest pre-computation to infer new facts that can aid induction, and it does not require computing loop-specific invariants. An instantiation of this technique is implemented in our tool Vajra. Please do refer to our paper at Takas. Thank you. Happy to take on a few questions.
Thank you, Devesh. We're almost out of time here, but I guess we do have room for a few questions. If anybody has a question, you can either put it on the chat or you can unmute yourself.
So if the loop has a break or continue statement conditioned upon a particular either one or multiple set of iterations, so does this work on those kind of loops?
So
Because
yeah,
those loops are discontinuous, I mean, in some sense, there is a discontinuity.
so such loops I believe can be transformed. So whenever there are continues and breaks, one can introduce a flag and put it as a part of the loop condition. So if they satisfy the grammar that we have for which we have supported, then we will be able to take care of such loops. Otherwise, we may not be able to. We do require that the given program satisfies several conditions. So there is a grammar that is outlined in the paper.
Okay, so that means that the only condition that you require is that you should not refer to the scalar or the array of p(n minus 1).
We need to know how many times the loop runs so that in the difference we can account for those many iterations. We also need to know that those iterations will be executed for the inductive proof to succeed. If so, the proof should not break in between. So that is why we need that continues and break statements are removed from the program and they are taken care of in the loop condition itself.
Okay, thank you.
Yeah.
Are there other questions? Don't see anything on the chat. If anybody wants to ask a question, you can either type in on the chat or unmute yourself. Okay. In case there aren't any, let us thank Divyesh. Thank you, Divyesh.
I
And
would like to I would like to thank the organizers for giving me a chance to give this presentation. Thank you so much.
yeah, welcome. Okay, so now we will move on to the next talk, which will be, so Divyesh, you can maybe turn off your video and unshare your screen. Yeah, and the next talk will be by Professor Kuldeep Meel. He will talk about the secrets of Ganak, designing scalable exact model counter. Ganak uh, is certainly among the most powerful exact model counters around today. And I just quickly want to introduce Kuldeep to the audience. So, Kuldeep Meel is the Song Ka Ke Assistant Professor in Computer Science Department of School of Computing at National University of Singapore. He is also affiliated with the Institute of Data Science, and he also holds a long-term visiting appointment at IIT Bombay in the Computer Science Department. His research interests are primarily at the intersection of AI and formal methods, and also trying to bridge the gap between theory and practice. His research group strongly believes and also actually acts upon these beliefs of developing mathematical frameworks whose faithful implementations can handle practical applications. He's a recipient of the 2009 NRF Fellowship for AI. So, Kuldeep, it's over to you. Thank you for telling us
Okay,
about Kanak.
thank you. Thank you, Supratik, for the introduction.
Yeah,
Thanks
can you
everyone for
turn on your
joining so early
video?
in the morning on Saturday. Okay, so let's get started. I designed the talk to be more like a conversation, so please feel free to interrupt in middle of the talk. You don't have to wait until the end of the talk. So I'll be talking about our exact counter Ganak, and this is joint work with Shubham Sharma, Mate Sus, and Subhajit Roy. Shubham was a master's student when he did this work, and Subhajit is affiliated at IIT Kanpur, and Mate is a long-term visitor in our group at NUS. Okay, so let's get started. And the first thing, quick thing that we want to get started with the problem statement. So as most of us have seen our last one day, we start with Boolean formulas. And the problem of satisfiability is to ask whether there exists a satisfying assignment. So is there a solution for a formula? In case of counting, we are interested in counting the number of solutions of a formula. So just to make sure we are on the same page, suppose the formula that was given to us is, let's say there are two variables and the formula is x1 or x2. So in this case, the formula is satisfiable. There exists a solution In fact, maybe you can assign x1 to 0, x2 to 1. That is one possible solution, right? There are also other solutions. For example, you can assign x1 to 1, x2 to 0, and 1, 1. So in case of counting, the problem is to count the number of solutions of this set. Okay, so we are interested in counting the number of solutions of this set, and a counter should return an answer 3. This is also called the problem denoted by sharp set. And this is the canonical Sharpie complete problem, thanks to Leslie Valiant's seminal work in 78. Well, since in this work, we focus on a slight relaxation of problem of model counting, where we allow the model counter to make mistake. In particular, what we are focusing on is probabilistic exact model counting. So given a formula F and some confidence delta, the counter should return an output that should be equals to the count with probability 1 minus delta. Turns out this relaxation does not seem, from complexity theoretic perspective, does not make the problem too simple. And it turns out the problem is still, from very complexity theoretic perspective, as hard as exact model counting, but I'll be discussing how this relaxation does allow us to scale much better. At this point, you might wonder, why should we care about this problem in the first place? Well, turns out counting is a very fundamental problem with wide variety of applications. In today's talk, I won't have time to go into details, but we have seen over the last few years applications from reliability of networks to quantified information flow, neural network robustness, and so on. And this also has led to a lot of counters that have been developed over past few years. Broadly, there are three categories of counters. There are knowledge compilation based, where you take the formula, you compile into a form where counting becomes a simpler problem. You can think of, if you could compile the formula into a binary decision diagram, then counting would turn out to be very simple. And based on this motivation, more refined forms have been proposed over the years. The other set of counters are search-based counters that look a little bit like, very much like the CTCL solvers, but instead of satisfiability, they are interested in doing counting. And this is precisely what we are going to focus on. Another line of work that I won't be focusing on today is approximate counting, where there is a long line of work on developing hashing-based techniques. So today, what we are going to focus on are going to be the search-based counters. And for the search-based counters, there are 4 ingredients that make them work. The first is decision process, something that we saw yesterday, but let me illustrate it more formally. So what you want to do is that, suppose at some point you have to count the number of solutions of this formula as stated here. So observe that if you can count the number of solutions of F and L and F and not L independently, then you can count the number of solutions of the formula F. So you can see that this is equivalent to formula F by just summing up the solutions of the two parts here, right? So as long as you can count the number of solutions of F and L and F and not L, then you can just sum up the number of solutions of these two subformulas and get the number of solutions of F. You can see that what we are going to do is that, given a formula F, what we can do is we can pick a variable, we can assign it some value. So we are going to call that as a literal. So let's say we assign L to be true, and we also can make it L to be false. And then we will just count the two separately and then sum up the two counts, okay? The second component that is important is called component decomposition. So in this case, if we can decompose the formula into components, so I'm going to call delta 1 to delta n components, such that none of these share any variables with each other. So if we can achieve such a decomposition, then you can observe that the count of a formula just turns out to be multiplying the count of each of these components. Just to make sure we are on the same page here. So suppose the formula that we were working with was something of the form x1 or x2 and x3 or x4. So note that these two components, delta 1 and delta 2, do not share any variables. The number of solutions of x1 or x2, as we discussed earlier, turns out to be 3. Similarly, the number of solutions of x3 or x4 is also 3. And then we can count the number of solutions of the formula just by multiplying the two, right? So what we are going to do when we are going to design the counter, we will look for the opportunities where we can divide the formula into components so that they don't share any variables. Okay. Now, finally, of course, we are going to, since as in the tutorial we saw yesterday, learning clauses is very important. So we are going to rely on conflict-driven clause learning. We'll learn the clauses as we go along. And finally, one very important part about counters is that we have to, instead of solvers where our interest is only finding one solution, in this case, we have to count over all possible solutions. So we'll often encounter similar formulas or similar components. And we would like to not have to redo all the computations. So we would like to reuse our effort that we have put in the past. So we'll be maintaining a cache. And this cache looks like for every component, the key is the component and the value is the number of solutions of the component. Okay. So these are the 4 key ingredients of search-based counters, and they appear in all possible, all the different variants of these counters. Let me illustrate the entire algorithm now. So what do we do? Start with a formula. Well, we pick some variable, right? So we pick a variable and assign a value. So this is just, decide one of the literal. We can decide whether to go for the positive or negative assignment first. So just like in the set solvers, we pick a variable, we assign it a value, which is a literal. So the first point is to take the L. Now, what we do is that we take the formula and we can now perform the unit propagation over F and L, right? So whatever literal we pick. Few things we can do is that if it turns out that this is empty, then we know that, well, the count is going to be 0. Otherwise, we try to look for the opportunity if the formula can be divided into components so that they don't share variables. If we can do such a decomposition, then we go through each of the components. For each of the component, we first try to ask, hey, do I have it stored in my cache already? If I do, then I just use the count. If I don't, then I recursively call the counter. Okay. And finally, once I have counted for F and L and F and not L, now I know the count for F, and I'm going to use this in the cache, right? So this is a recursive process. As you can see, first we start with the formula, and then we go in the one side of this search space, get the counts over there, then we go in the other part, and we combine the two counts, and in our cache, we store the formula as well as, because the formula entirety is also just one component. So a component, just to make sure we are on the same page, is just a set of clauses. Okay. And then finally, the count that we get is the count written at the very end of the run of this algorithm. Okay, so that's what all the counters look like. As you can see, just like CDCL algorithm, the overarching framework is usually very simple. The magic, of course, lies in How do you make the decisions? How do you search for the components and other parts about restarts and so on that I'm going to discuss later on. Okay, but this is kind of the core algorithm that we have for counting. At this point, any questions, quick questions about the algorithm? Okay, so I guess there are no questions. Let me move on. So let's probably start with a simple example. Okay, so let's say here is the formula that I have. This formula has three clauses, x1 or x2 or x3, and x1 or x4 or x5, and so on, right? So let's try to ask, is it possible that I can divide the formula into some components so that they don't share variables? Not. See, the first and second clause share x1, right? And in fact, the third clause also shares the same variable, x1. So I cannot divide this into components that they don't share any variables. Well, okay, so what do? I go and pick a variable and I make a decision on that. Okay, so let's say I say, let me assign x1 to be true, right? So the literal is x1. And now I get, once I assign x1 to be true, then I'm going to be looking at, so let's see, what do I have to look at? Well, if I assign in this formula f, if I assign x1 to be true, then I look at the clause x2 or x3, right? This is the clause that I have, because x1, assigning x1 to true would make not x1 0. Remember, these two clauses are completely satisfied. But one thing that you need to remember at this point is that the residual formula that you are left with is x2 or x3. But we were originally working with variables x1 to x5. And in this case, we have assigned the value to x1, but x4 and x5 are unassigned, right? So we need to kind of remember that what we want to do is to count over all the variables in the original formula. So in this case, we have x2 or x3, and the x4 and x5 are the variables that we haven't assigned because they kind of disappear from the residual clauses that we are left. Okay. All right. So now we go, and as you know, x2 or x3 has the number of solutions for x2 or x3 is 3. But if you want to look at the number of solutions for x2 or x3, where we are also interested in these variables that are not assigned, then the number of solutions turn out to be 3 times 4. Okay, that turns out to be 12 because x4 and x5 are just free variables hanging around. All right. So that was my one branch. Now I go back and I say, okay, let me assign x1 to false. If I assign x1 to false, then this clause is satisfied, right? So we don't have to worry about. But by assigning x1 to false, I can break it down into two clauses, x2 or x3 and x4 or x5. Okay. Well, now I can partition this into components that don't share variables, right? Because x2 or x3 and x4 or x5 do not share any variables with each other. So now I can recursively call count on x2 or x3 and x4 or x5. What about x2 or x3? Well, x2 or x3 is in my cache here, right? So instead of having to count again over x2 or x3, I can just simply do a lookup and I can obtain the count for x2 or x3. In case of x4 or x5, of course, it's not in my cache, so I will have to do the count again. That again turns out to be 3 once I do the count, right? So in case of x2 or x3, just by doing the cache lookup, I get the count to be 3. For x4 or x5, I go and figure out the count. This turns out to be 3. In that case, we get the count to be 9. And then earlier, we had the count from here to be 12. So finally, the count turns out to be 21. Okay. So this is how the entire algorithm continues. Any questions about how the search space counters work? So the idea is that you pick a variable, you assign it, you get the count, then you assign the negation of it, you get the count, you sum them up, and as we go along, we do want to maintain this cache so that we can reuse some of the computation that we do. Okay.
So, yeah, in particular for this formula, it seems that this choice of x1 is quite beneficial as compared to other literals. So, what are the heuristics typically people look at while choosing variables to split on for counting?
Yeah, that's an excellent question. So we are going to get into the heuristics. So the name of the game in set solving and related areas is heuristics. So I'll quickly get there to the decision heuristics. Yeah. Okay. Okay. So as Saurabh alluded to, that the heuristics are going to be important. And what we did is, as I mentioned, that there has been already a long line of work on these search-based counters. So we looked at these counters and we said, well, let's look at what are all the heuristics that we can improve upon. And in particular, we make 5 contributions. One, we looked at cache because we can see that cache is important. So probably we would like to have a more efficient cache, maybe in terms of memory. Then we need to figure out how to branch. And the third thing that I keep telling is that you pick a variable and you have to figure out whether to assign it true or false. So what phase you assign it. And then another 2 contributions that were motivated from developments in other areas, and that I'm going to discuss about independent support and learning and starting over. Okay, so let me get into the business of heuristics now. Okay, so first is, how do we have the maintain cache in memory? Well, we get a formula, and as I mentioned, the key is the formula itself, or what we call as component. So long ago, in 2005, the first scheme that was proposed was to say that you sort all the clauses in order of their variables, or in order of their increasing IDs. So you use some sort of sorting of all the clauses, and then you encode the components just by having a string of the literals that appear in it. So one encoding is to say, well, if you are familiar with the Dimex format, then this will look very natural. You are just encoding the clauses over there, right? So you say -3, -5, 6, and then similarly -1, 4, -6, separated by 0. Okay, so this is just take the formula and think about get a Dimex representation. You just want to make sure that there is some sorting so that you get the unique representation every time you call the scheme, and then this will be your key. As you can guess, this can become very large if we had to deal with formulas involving hundreds of thousands of variables. This is going to be really large, so you don't want to keep storing it. So then Mark Thurley in 2007 proposed what is called hybrid scheme. And the idea was that what you want to really store are the set of variables and the set of clauses. So all you want to store is their indices. You do not have to store the clauses by themselves. Okay, so the idea was that you store the variables that appear in these clauses and then the indices of the clauses that appear here. So you say, well, the variable that appear are 1, 2, 3, 4, 5, 6, and then the clauses that are in my component are clause 1, 2, and 3. Okay.
So Kuldeep, just having the identities of the clauses should be sufficient, right?
So the the reason that, remember, the component is once you assign a variable, if you, let's go back here, x2 or x3, right?
Yeah.
So we need to remember that x2 or x3 was not in the original clause. This is a we get after assigning x1 to some value. Okay.
The identities of the clauses are the identities in the original formula, right?
Yeah.
So in the original formula, there is no clause called x2 or x3.
Yeah. So here now the idea here is that all you want to store is that the how we can encode this component is to say that it comes from C3 and the variables that appear in this clause are 2 and 3.
Oh, I see. I see. So you're saying the subset of the clause. So when you say C3, it is not just C3.
Yeah.
Some subset of C3.
So at all points, we are talking about the residual formula. So where the original formula and some of the variables have been assigned, now we get these components and we want to figure out how do we want to store them. Yeah, sorry about not emphasizing that earlier.
No, the residual formula can happen because you choose a subset of clauses also. But
No,
what
yeah,
you're
in
saying,
this case, the search is based on the variable. So you have made assignment to variables. And now you want to talk about the clauses have been reduced because of the assignment to the variables.
right. So to find the residual formula, I have to look at the clauses that are there in that whatever hash key, and then retain only those parts of the clauses that are in the variables, in the
Yeah.
list of variables. Okay.
So one thing that you might observe here is that when we are doing the hybrid encoding, we are losing a little bit of a precision. How so? Well, as we discussed earlier also, we had two clauses, x1 or x2 or x3. Let me just quickly illustrate. So let's say we had these two clauses. When we assign x1 to false, right? Then in our residual formula, the only clause that gets left, so let's call it C1 and C2. So we have the clause C1 here. And the variables that occur are 2 and 3. In case when we assign x1 to true, then the clause that is left is C2. And the two variables that appear, there are again 2 and 3. But you see, the hybrid encoding would not be able to figure out that in the residual formula, the clauses that the residual formula is equivalent, right? In both the cases, you just get x2 or x3. But the encoding that is proposed here loses the precision, and you will say, oh, in one case you have the clause C1 with variables appearing 2, 3. In the other case, you have clause C2 with variables appearing 2, 3. So if you just try to compare these two strings, then of course you will say that they are probably different components. So it is sound, but it loses precision, right? So if two strings are same, if you have the set of clauses and the set of variables that appear there are identical, then of course the two formulas, the residual formula is identical. But it may happen that the strings are not same, but the formulas that you have are still identical, and you lose a little bit of precision.
So why do you lose precision here? I mean, you lose efficiency here, but why precision? I mean,
Okay. So precision is just generally from the perspective of efficiency. So I think I should be clear. It's not about the count correctness,
huh.
but the precision in terms of your calls. Okay. So maybe let's call it efficiency just to,
Okay.
yeah. So we kept the story going. We said that, okay, let's try to lose efficiency a little bit more in the sense of that we can try to have smaller cache, and it may happen that sometimes two components may be equal and we may not be able to identify them. However, we said that maybe we can also lose a little bit of soundness in the sense that we may say that the two components are equal and they may not be equal. And At this point, it becomes clear what we were looking for is to be able to use hash functions. So instead of storing the string, we would hash these strings into buckets, and we are only going to do the match over the hash function, the hashed values. Now, this allows us to store, have the cache very compact, but at the loss of precision, because now it may happen that the hash values match, but the formulas are not equivalent. And that requires us to go from exact counting to probabilistic exact counting. So the answer that we written might be wrong. Okay. It turns out that there is a very efficient library available in C, a C++ CL hash that takes about only 1 to 2 CPU cycles to compute this hash. So this turns out to be fairly efficient to implement. Okay. So this is the idea about component caching. We want to get more efficient caching, and the idea is not, instead of storing these strings, maybe the standard or hybrid encoding, we store their hash values, and we use universal hash functions to store that. And we can do theoretical analysis that allows us to quantify how much error we can make. And this process of going from storing the strings by themselves to storing their hashed values also forces us to go from exact counting to probabilistic exact counting. Okay. Right. So now let's move to the second part, which is that which variable to choose from. Well, the standard algorithm that is used is a combination of visits and DLCS. So these are visits is what Armin discussed yesterday, which is variable state independent decay sum. So this essentially tries to prioritize variables that are in the recently generated clauses. Okay. While the DLCS tries to prioritize variables that are the most occurring variables in the residual formula that we have. Okay. And the algorithm that was proposed by Sang et al. And then improved upon by Thurley was to say that you somehow do this weighted combination of these two scores. Okay. What we observed here is that these two algorithms don't kind of keep track of what's happening in the cache. And you can see that the efficiency of these counting algorithms would depend on our ability to reuse as much work as possible. So if there are some components in the cache, and if we can somehow reorder or search in a way that we can get more cache hits, then we'll be able to reuse a lot of work. Okay.
So Kuldeep, before we move ahead, there is one question on the.
I can see the questions. So
you have seen.
Yeah. Let me come back to this question. This is a very good question. I'll come back to it in the later half of the talk. So what we propose is to go from VSETs to CSV set, where we also said that we should also look at cache. And how can you look at cache? Well, if you see certain variables that occur very often in the component cache that we are maintaining, then what we would like to do is that we would like to not make decision on those variables. Why so? We can go back to our example, right? Let's say I told you that in the cache, X2 and X3 occur very often, okay? And you have this formula that has, other clauses also, right? And if I tell you that X2 and X3 occur very often in cache that you are maintaining, then if you make a decision on X2 or X3, then that variable goes away, right? The moment you make decision, then in the residual formula, that variable will not appear. So what you want to do is that you would like to make decision on the variables that don't occur so often in cache. Okay. So the heuristic that we propose is to say that, well, let's do a weighted combination of V sets, which is more about what's going on in the search right now, and a combination with the cache score, which is the cache that we are maintaining, so that we can direct the search in a way to get more cache hits. Okay.
So did you say that if it is appearing in the cache often, you're going to penalize it or you're going to bump it?
If it is appearing often, then we would not like to decide on it. So in terms of our score, we would like to give. So that's why we do this weighted combination. So we would penalize it. So the more it appears in the cache, the less we would like to decide on it.
I see. And what exactly is the rationale for that?
Between these alpha and beta.
No, no. I'm saying that if it appears more in the cache, it also probably means that it was playing an important role, right? Because you were.
Yeah, so this is kind of, that's why just one of them does not turn out to be very efficient. And
Hmm.
you had to kind of balance the two.
So I was just interested in the rationale. I think you said something, I missed it.
So the
Why?
rationale is two parts, right? So somehow we think that the V sets, what it is doing is that it is prioritizing the search process. So it is allowing us to kind of go towards the solutions, because it's a large space. So there are a lot of parts of the search space where there are no solutions. So V sets is prioritizing us going towards the solutions. And cache score, once it goes towards the solution, it prioritizes how we explore the solution space, right? So that we can get more cache hits.
I see. I see.
Okay. But as is true for most of these things, we don't have very rigorous theoretical explanation, but this is kind of our intuitive understanding.
Sure. Sure. Thanks.
Okay. There is another question from Rigovin, which is, how big a formula do you cache? Well, as you can see that our cache scheme now, we only store the hash values, and you can, for everything, we can just convert into a 64-bit hash. So we can now, it's very easy to handle formula that have few hundreds of thousands of clauses. So cache is no longer much of an issue, just in terms of the memory. Of course, the formula can be hard to handle. Okay. So now in our cache, we are only storing the hash values. We are not storing the formula anymore. Okay, so let me move to the third heuristic, which is, we have decided that we want to pick on variable x1. Should we assign it true or false? The heuristic that is used, and I was very surprised when Armin mentioned about dailies yesterday. So what it does is that it looks at the residual formula and it says that which variable occurs more often. Sorry, it looks at the residual formula, and then for x1 it says whether x1 occurs more often as positive or negative literal, right? So it says that let's look at the residual formula and let me figure out if x1 occurs more often as positive, or it occurs more often as negative. If it occurs more often as positive, then you say, okay, I'm going to assign x1 to true. Otherwise, I'm going to assign x1 to false. What we observe is that this check about greater than equals to, this is very brittle if the two values between the two are very close, right? So what we do is that we want to reduce our trust on dailies by adding a little bit of randomness when the two values are very close to each other. So suppose for x1, for a literal L, it occurs, L occurs 2 times and not L, or maybe 20 times and not L occurs 19, then we say that this check may not be so meaningful. So at that case, if the difference is not high, then we also allow a little bit of randomness by allowing it to randomly decide between the two. Okay. So that's our third heuristic. So remember, things we had done. We had to maintain cache, then pick a variable, figure out. So we have now we are picking the variable depending on what's happening in the cache, and then we have to figure out which value to assign true or false, which is also called fetch, and we assign it based on how often the literals appear in the residual formula, but also a little bit of randomness when we cannot really trust this check between greater than or equals to, right? So in some sense, we are smoothing it. So so that if the difference is not very large, then you just want to allow a little bit randomness.
So what does PC stand for?
This was just phase selection. We couldn't, we call it PC, but that's just
Okay.
because of the acronyms in the paper. Yeah.
Sure.
It would have been nice to call PS, but that was just the way we were naming things.
Okay. Okay.
Yeah. Okay, so now the fourth thing. So the three things were mainly based on looking at the algorithm and trying to improve the heuristics. The last two components that we added on the search-based counters are motivated by progress elsewhere. And one of the concept is the notion of independent support. So what is an independent support? Well, independent support for a formula says that it's a subset of the variables of the formula, so that if two solutions agree on the independent support, then they must be equal. Okay, so maybe let me give a quick example. Suppose the formula that we have encodes something like this. It encodes x3 if and only if x1 or x2. Okay, then you can see that once I assign values to x1 and x2, then the value to the rest of the variables is uniquely determined. So if two solutions agree on x1 and x2, they have to agree on rest of the variables, right? In this case, x3. So x1 and x2 turns out to be an independent support. Okay. So the idea is, if two solutions agree on independent support, then they must be equal. Okay. So once we assign the values to the independent support, for rest of the variables, either there is no assignment to the rest of the variables such that you have a solution. This the assignment to the independent support can be extended to get a solution, or there's a unique assignment to rest of the variables. Okay. So the notion of independent support has been found useful in the context of approximate model counting. And we were thinking that what can we somehow use it for exact counting as well? Well, if you think more about it, it says that maybe what if we just try to assign the variables in the independent support first? Once we can assign the variables in the independent support, then perhaps for rest of the residual formula, all we want to do is to do a quick set or an unset check, right? We just want to figure out, hey, is there a variable to rest of the, is there an assignment to rest of the variables so that the residual formula can be satisfied? If there is, then I know that the number of solutions of the residual formula is 1, otherwise 0, right? Once you assign all the variables in an independent support, then for rest of the variables, either there is unique assignment or there is no assignment that satisfies the formula. Okay. So what do? We start with the formula and we say that, again, this kind of ideas turn out to be useful when the instance is hard. So if the instance turns out to be hard, for which we measure based on how many conflicts we have seen, so then we say, okay, let's first compute the independent support for the formula. And computation of independent support, there's an existing algorithm that we can use. It does turn out to be expensive, so we want to use it only when the instance is actually hard. And once we compute the independent support, then we perform the decision process on variables from the independent support. Okay. So once we have decided on all the variables in independent support, then for residual formula, all we want to do is a quick SAT check. Okay. We just want to figure out, is there a solution or not? If there is, then the model count for the residual formula is 1, otherwise 0. Okay. So the usage of independent support now turns the counting algorithm into two parts. Assign the variables in independent support, so you are somehow performing counting over that part of the search space, and rest of them becomes the SAT calls that you are doing. Okay. Right. So finally, the last heuristic that we use is the idea more inspired from random restarts. So as Armin talked yesterday, that somehow these random restarts are very useful. Of course, there's a lot of debate whether they why they help, and the recent conclusions seem to suggest that they help more in case of unset, which is very interesting since they were originally proposed to help more in case of the set instances. Well, in case of set solvers, it kind of makes sense to use a restart, right? You are not making a lot of progress, so you hope that maybe a quick restart might help. But in case of counting, it seems a bit counterintuitive that restart would be helpful, because you have to somehow explore the entire solution space to count. So you feel like if you just go back, then you are going to lose a lot of work. That intuition is correct, but then restarts also help you to understand something more about the formula. So what we did is to, instead of doing restarts again and again, we say that let's initially start the search, and after 5,000 decisions or so, we are going to restart. Okay. But we don't want to forget everything. So in particular, what we do is that we are going to remember all the scores that we have obtained. Okay, so we have, and now at this point, we have the scores for the cache score, VSIT score, the activity scores. So we maintain all the scores so that now when we start again, we'll be able to possibly have a better ordering of decision variables. Okay. The number 5,000 turns out to be fairly tunable, and again, we don't see much difference if we tune it to some close by values. Of course, you don't want to restart after a very long time. Okay, so you want to do a quick restart after a few thousands of decisions, and then you want to remember all the things that you learned about the search space so that you can have better ordering of decision variables.
So, Kuldeep, there is another question in the chat.
So Saurabh's question is, what about component deletion strategy? So right now, we maintain the score for the components, and we just use the LRU scheme, which is that whatever is the least recently used stays and others go away. Yeah. So okay, so what we did, all these five things we put together into this state of art search based counter sharp set, and the new counter we call is Ganak, which for Indian audience is not very surprising. This Ganak stands for count in Hindi. And as I mentioned, since we are using probabilistic component caching, so it turns out that we, instead of giving exact count, we have the probabilistic guarantees here, right? So in particular, the count that we are returning is correct with probability 1 minus delta. Delta is the parameter that is specified by the user. Once user gives us the parameter, that allows us to decide what should be the size, the range of the hash functions we are using. Okay, so the closer the confidence you want, you would want to use larger range for the hash functions. Okay, the tool is available open source. So let me now discuss experimental evaluation. So again, we took the standard set of benchmarks that are available for counting.
So Kuldeep, I have a question.
Yeah.
So, so if you can go back to that slide on the probabilistic guarantee, yeah. So, so how do I use this counter in the sense that so any probabilistic counters, they'll have to be run multiple times and some averaging has to be done, some statistical averaging, right? So for the exact count, how would I do that? So I run it multiple times and then I take the majority consensus or something.
No, the way the algorithm is implemented from the user perspective, all you have to do is specify the confidence.
Yeah.
What we do in the algorithm is based on the confidence, we figure out the range of the hash function that needs to be, what should be the range. So you can see we are caching these components right from the space. And if we use a hash function with very small range, then we might get a lot of collisions.
Yeah, yeah. No, but so it's a single run, is it? You're doing?
Ah, so we are doing single run, but the well, not exactly a single run. So we first determine the range of the hash function, then we finish the run. We see how many components did we see in the entire run, and from there we determine if the range that we selected was correct or not. If it was not correct, then we'll have to do the doubling.
No, my question is something different. What I'm saying is finally, whatever count you report, you will have to say that the probability, the count, the the probability that your answer is correct is greater than equal to 99%
Yeah.
something. So all I'm saying is that suppose yeah. So I mean, all of these probabilistic counters. Basically, if I run it a second time, I might get a different answer,
Yes.
right? So now, if I'm running it three times and I'm getting three different answers, or if I'm running it 3,000 times and getting 3,000 different answers, uh, you know, how do I? I mean, is there any way to sort of?
You can do it at two levels, right? Either
Hmm.
you can run it with low confidence, so you can say give me an answer with confidence 0.95, and I'm going to get multiple answers, right?
Multiple runs producing multiple answers.
Yeah.
Yeah.
Or you can say that every run should produce an answer with confidence 0.99. I want an answer with confidence 99%.
Yeah, yeah. So what I'm saying is, that, okay, I don't know if I'm articulating it properly. So what I'm saying is that whatever probability you choose,
Yeah.
it's going to give you something from one run or two runs, as you're saying, right?
Yeah.
And so I think the thing about probabilistic algorithms, randomized algorithms, is that you can then run it multiple times, and then you can do a probability amplification by taking some kind of an aggregate, such
Yeah.
statistical aggregate. So is something like that? Does it make sense here? I mean, it ideally should, right? I mean, you have a randomized algorithm here.
Well, yeah. So I mean, this is true for any randomized algorithm, right?
Correct.
You can repeat it multiple times.
Uh,
But if you want to do probability amplification, the calculation that we are using are union bounds, but they turn out to be much stronger. So if you want to get a higher confidence, it's much better to just ask it directly to the counter, because the amplification that we are doing is based on the size of the hash range.
Yeah. So I was interested in what is the kind of statistical average that one would do. I mean, suppose, of course, I can specify to Ganak and it computes a larger range.
Yeah.
But suppose I were to sort of run it and then compute an aggregate, what is the kind of aggregation? Because
Oh, okay. Yeah. So in this case, you could use the majority, right?
major, right?
Yeah. You could use the majority or just the median.
Median, I'm not sure because I mean,
Yeah. So
what?
in this case,
So
sorry, you will have to use the majority because you are getting a
so
point.
isn't it the case that because of the collision you are always going to overcount? There won't be any undercounting, right? So that means that when you do this probabilistic exact model counting, your count that you might report is always going to be higher than what it is.
Not really, because you suppose you have a component, these two things may uh, collide, right? So suppose you wanted to find the count for x4 or x5, and you do the lookup and it turns out x1 or x2 or x3 was there, right?
Okay.
Or the other way. So you want to find the count for x1 or x2 or x3, and it turns out, it collides, the hash of these two collide. Okay. So the count for this is, you know, um, 3, and this is 7. So it can be either way.
Oh, oh, okay.
Yeah.
I thought that there will be double counting when the collision is there. So
No, you are saying that I'll just trust whatever count is for the key, right?
I see, I see.
Yeah.
Okay, yeah.
Yeah. So delta is another question on chat. It is indeed based on the probability of hash collision. So what it says is that the probability of any collision is less than delta. So our analysis is very conservative. That will become clear very soon. Okay. So now let me discuss the experimental evaluation. Okay. So what we did is that we set delta to be 0.05, so which implies that there was a 5% chance of us making a mistake. We compared it since we implemented Ganak on top of sharpset, so we compare with sharpset. And as you can see that we are able to solve about 50 more instances than sharpset, which is usually significant for these kind of problems where making progress is usually hard. And what was also interesting, and which I think points to conservative nature of our analysis, is that the model count that we got in all of this is exact. Um, so we did not, Ganak does not make any mistake. So maybe I can about the theory, maybe I'll wait till the end of the talk and probably can go in a little bit more detail. So it's kind of based on very simple analysis of universal hash functions.
but Kuldeep, how did you figure out that the count was exact for the cases where SharpSat didn't run?
Ah, okay, you are absolutely right. So this was exact for all benchmark for which we had counts. So all benchmarks were sharp set finished.
Ah, okay.
Yeah, assuming no bug in sharp set, right? So.
Hmm. Okay.
Okay, so now let me get to the part I guess all of you have been waiting. I talked about 5 different improvements, and the natural question is, how do these contribute to the performance? Okay, so this is a heat map. Let me to explain how this is working. So on x-axis, we have done this bit encoding. So what does it mean? So let's try to decipher this part. So this says that PCC, which was the part about component caching, that is 0 implies for it was disabled, 1 is for turned on. So it says 1, the decision heuristic that I proposed, CSV sets, was turned on. And then 0 was for the fetch selection that was turned on. Okay. This was based on the polarity caching fetch selection heuristic that I talked about is turned on. Okay. Similarly, on y-axis, the first bit is for independent support and the second bit is for the learn and start over. And I think there is something that I really liked about the entire project, and probably it was a very nice learning experience from research perspective, because we started working on developing all these techniques. And let me show you how what happens. So let's talk about first the probabilistic component caching. So this is the combination of the solver where all these heuristics are turned off, right? So this is what sharp set would behave like. And here is the combination where all the different all the heuristics are turned on. Okay, so this is Ganak, the comparison that I just showed. And let's try to see from here. So the scores that I'm showing are part 2 scores. This, as Armin talked yesterday, this is penalized average runtime, where if an instance times out, then you penalize by twice of the timeout. So we run all these experiments on 5,000 seconds. So if something timed out, then we penalize by 10,000 seconds, and here is the average time. Okay. So what happens when we go from 3020? So let's try to see what happens when we just turn on component caching. Okay. Improvement of 12 seconds, not very significant. Okay, so on its own, it looked like not a very significant idea. What happens if we turn on the decision heuristic? Well, improvement of 12 seconds. So not, again, very interesting. Okay. What about component caching? Well, improvement of 5 seconds. Okay. So not very interesting. What about learn and start over? Okay, for all our hopes of improvement, there's a slowdown of 5 seconds. What about independent support? Well, this was a huge jump. Okay, so we improved by 500 seconds. But then it turns out, as you can now see, that all the blocks tell us different pictures. But it turns out that if you combine the independent support with other heuristic, then we can go from 2495 to 2359. So this is really the case where the sum is, the whole is greater than the sum of its parts, right? All the heuristic on their own seem like they are not improving much. But when you combine all of them, then we start seeing a significant improvement. I guess I will have to tell you that we don't fully understand why they work so well in conjunction with each other. But this was very interesting in the sense that when we combine all of those, we can get a very significant improvement. And it's also very instructive to start looking at, again, different combinations. So for example, if you turn on the independent support, right, And now you say, okay, let me try to turn on, just let's say you want to again just turn on the probabilistic component caching. And then the improvement that we are getting here is about 100 seconds, more than 100 seconds. So suddenly it becomes more powerful when the independent support kind of takes care of these hard instances, and then the component caching can start shining more. So um, there's of course a lot more analysis that needs to be done. And it was very interesting that when you combine all these heuristics, the performance becomes much better. We were very happy. This year there was a model counting competition, and our entry based on Ganak did win first in 2 out of 3 tracks. So these heuristics are interesting, and there's opportunity for a lot more analysis that one needs to do to understand what is going on. So I think what we have seen so far is there's opportunity by looking at different components of these exact counters, and we propose some heuristics more. And while we propose for these search-based counters, I think one interesting line of work would be to see also for knowledge compilation-based techniques if we can see such improvements, and also being able to understand much better what's going on, why, how these different heuristics work in tandem with each other. So with that, I would like to conclude the talk. Thanks for listening to the talk this morning. I'd be happy to take more questions. Thank you. So maybe I can quickly now go back to questions from Govin.
Yeah, I think so.
So that's a very good observation, which is that can you do, and Govin's question is that X1 or X2 and X3 or X4 have the same number of solutions, and there is also, if one can look at, there is some sort of isomorphism here, right? If we could just relabel the variables, then we would be able to get the count. It turns out, yes. However, computing this isomorphism has a cost. And in our new paper, which is supposed to appear at AAAI next month, we indeed went forward and implemented isomorphism. And it turns out that it helps in combinatorial instances where checking for isomorphism pays off. But if you try to apply for most of the other instances, then checking for isomorphism has a higher cost than what you are saving when whenever you get a hit. You save on the computation, but remember, every time you pay off, you pay the cost of checking for isomorphism. So this is the strategy works really well for combinatorial instances, but we haven't seen much improvement for general instances. But for combinatorial problems, we can see a significant improvement. There was another question about cache size. For these experiments, we put cache size of 2, if I remember correctly, then for 2 gigabyte. There was also a question about, there is a very nice question again. Is there a certificate? Yeah, this is a very interesting problem that is being looked. There are others in community who are looking into it. There is some work, but we don't fully understand what it means to, how do we certify that the count is correct. So should the counter return some sort of trace, just like SAT solvers that you can check later on, or somehow you give the count and you can try to verify. There was one line of work that we did in AAA 2019 along with Supratik, where we looked at probabilistic verification. So if you tell me that here is the count, then with some probability and some approximation, we may be able to say that, yeah, the number that you're given is within factor of 2 or so. Okay. So this was the work at IIII 2019. The paper is on the hardness. So that's the title. Let me see. Yeah, so I think if we have a little bit more time, I can also quickly tell you what the analysis is. So what we want to do is that at every point we were doing the lookups, right? You want to say that for all these components, you want to figure out what is the probability that for. So let's say this was the sequence of all the components that we generated. So we want to analyze what is the probability that the hash of these two components match when they are not equivalent. Okay. The hash function that we use are what are called epsilon universal hash functions. So something of this form. So if they are, if these hash functions are hashing from over the space of components to R buckets, then the probability of such a collision is epsilon over R. And what you would want is that you would want to make sure that there are no collisions. So you would want, over all these pairs to be less than the delta that you have specified. And from there, we can compare to what should be R. Okay. So rest of the analysis is of course in the paper, but that's kind of the core idea about the analysis.
So are there other probabilistic exact model counters around, or this is the only one?
This is the only one right now.
I see. So, kind of perhaps tangential question, but really the probabilistic part here comes from the probabilistic caching.
Yeah.
Right? Now, I guess caching is used in a lot of other uh, tools as well, uh, right? I mean, a lot of other tools in similar problem areas. I mean, for example, I guess when you build decision diagrams, also uh, when you do knowledge compilation, right? Then also sometimes then also caching helps. So has it been used in that context? And I don't even know what it means to come up with a compiled form for which we say that there is a probability that that is correct.
Yeah, that's an excellent question. And I think one one thing that I guess I did not give enough credit was this C++ library called CL hash, which is this amazingly fast library to compute this hash. Um, and this was a recent development in 2016,
What is
2015
the
or
hash
so.
it computes?
Sorry?
What hash function does it compute?
It computes the hash function for which the guarantee is a little bit weaker than pairwise independence. Okay. So in case of pairwise independence, you would have something like 1 by R. And in this case, you have something that is slightly larger. I forgot some factor here. So it's like 1 plus epsilon.
I see.
And so there is a small constant uh,
So this
factor
is
that is
okay.
slightly
So this
large
you can look it up. But this is in which library of
in C++.
no? What it is in STL or where?
Yeah, I mean, you can, I think it's available just like a STL. You can, I think one
Okay.
of the C++ versions allow it.
Okay.
So, with availability of this library, because the reason I wanted to mention that if you try to implement your own hash function, then the computation is a issue. When you are computing the hash, that takes time. But I think availability of this library should allow us to look at other places where you are using hashing, and you can ask the question that maybe we should look at probabilistic hashing. In case of knowledge compilation, I think this is what it would translate to, that the compiled form you obtained is represents the original formula with high probability. So there is a chance that what you obtained is completely wrong.
Yeah, yeah.
But I think, and I guess what you can do is that you can get different forms and probably try to check their equivalence or so to build more confidence.
Okay.
But to emphasize that how important it gets is that you could ask the question the other way. When you had turned on all the heuristics and let's say you just want to turn off the component caching, then you do get which is fairly significant hit of about 110 seconds or so.
So what is not clear from this heat map is what if you did not do probabilistic component caching but just used one of the things, whatever, HC and something you said, no, STD or something.
Yeah, so this is exactly this is what it would correspond to, right? You disable the probabilistic component caching part here,
Hmm.
and all the other heuristics are turned on.
No, but instead of the probabilistic component caching, if I had used deterministic component caching.
Yeah, so when I say that we had disabled probabilistic component caching, then the default is I think I forgot to
Oh,
specify.
yes.
The
Oh,
default is indeed HC.
oh, I see. Okay. Okay.
So then we get a hit of about this 115 seconds, right?
Okay, great. Yeah.
Yeah.
So are there
Okay.
other questions? I think Manoranjan had a question, or maybe you've already answered that.
Yeah.
The theory behind probabilistic analysis. I guess you explained it very briefly.
Yeah.
Uh,
I'll be happy to discuss offline more.
yeah. So I think if there are no further questions, maybe we'll end the session. And
Yeah.
of course, the
Thank you.
Discord rooms are open. So Kuldeep, if I can request you to be there for some time if people have more
Yeah.
questions.
Certainly.
And then we will the afternoon sessions by Martin Nick's Brain will start at 1:30. I request all of you to come around maybe 1:15, 10 or 15 minutes earlier, so that if there are problems with the Zoom setup, uh, we can fix those. So see all of you in the afternoon, uh, afternoon Indian time. Yeah, I'm sure this is different parts of the world, it's different times. And I guess the Discord room would be the right place to go and have some more chat with Kuldeep.